to the atmosphere, will it not create a net force on it? So, the answer is that atmospheric pressure acts on the exposed portion as well as the immersed portion. So, that is how it cancels off. So, that answer is as elementary as this answer, where you were holding on to the biometric device. You have given it? So, we have moved on to setting up the equations of motion. Like in the problem of hydrostatics, where you determine pressure distribution, then integrate pressure and find forces. So, pressure is distributed. So, pressure at a point, when you determine pressure at a point, it is an example of local solution, obtaining a detailed solution, a local solution. So, pressure is a local variable. When you integrate pressure and get a force, it is a single force for the entire, let us say, gate or surface or the object being studied. So, that is the opposite of local is global. So, force is a global quantity. Similarly, the point of action of that force is also a global quantity. So, the approach we have adopted is to get the local solution, integrate and find the global solution. So, later we will look at some simple examples where we find the global solution straight away. When you do that, you will also realize that you can't find local. So, local to global, that is a one way calculation. Global to local is much harder. Okay, it is like saying class average is, should I say 8.9? But I can't, from that number, I can't really find out what is his CPI. Right? But if you give me the CPI of every student, I can find the class average. That is local and global. So, the approach we have adopted is in hydrostatics, find pressure and then find forces. So, once the fluid is in motion, the unknowns are velocity and pressure. So, the equations of motion will determine velocity and pressure. From these quantities, you find the stress tensor. From this quantity sigma, you find forces and moments. This is the overall approach adopted in fluid mechanics. Some exceptions for some simple problems, you may be able to skip the intermediate steps and get the global answer straight away. But by and large, this is the approach. So, solid mechanics also has a very similar approach, where velocity is replaced by displacement. But there is a very significant point of difference, which has to do with the natural laws being applicable for a certain amount of material, which we call a region with constant mass. So, the representation is you have a flowing medium and you set up a control volume in it. This CV is fixed in space, it is bounded by a control surface. The control surface is defined in terms of the unit normal. Now, the natural laws cannot be applied to the matter contained in CV, because flow is continuously taking place. One particle gets substituted by another. So, by reference to the example I gave you last time, wherein force is applied to a fixed particle, sum of all forces equal to mass times acceleration, that could be done for that given particle, solid particle. You can't do it in a fluid medium, which is a collection of particles. They are all moving from one point to another, and their movement depends on velocity, which is an unknown quantity. So, here we make use of a very important result, again we discussed it last time, called Reynolds transport theorem, which relates quantities for the material contained in CV. So, that is called Cm. So, we define the attributes of the material contained in Cm as capital phi defined over Cm. Now, the definition is at the present time instant t. So, small phi is capital phi per unit mass, sometimes called the intrinsic value. What are the attributes? The attributes relate to the natural laws that we are going to employ to set up the equations of motion. So, at the continuum scale, they are conservation of mass, Newton's second law of motion. We never say conservation of momentum, we always say Newton's second law of motion. And third is, again we do not say conservation of energy, we say first law of thermodynamics, and there is also a second law of thermodynamics in the background, which directs the processes taking place in the flow field. So, this Cm is equal to Cv at the time instant t. So, the evaluation is really done with respect to Cv and Cs, but the definition of capital phi is with respect to the material contained in Cv called Cm, constant mass. So, if you write this derivative, it is the right hand side evaluated at Cm time t plus delta t minus the same integral Cm t divided by delta t, limit delta t approaching 0. That is the definition of a derivative. That is how it has been done in the book, but I gave you a very important result called a Leibniz rule, which helps you write or evaluate the right hand side in one shot. So, when you say Cm t plus delta t, that is the material which has now gone out of Cv, that matter has gone out. So, how rapidly is it going out? It is going out at the speed u, the fluid speed u. Okay. So, every part of it is moving Suppose you consider a small element here, it is ds, it is moving out at a speed u, where u is the local fluid velocity. So, then when you evaluate the integral, either longhand, one is a longhand approach, by writing derivative as delta phi over delta t in the limit delta t approaching 0, where delta phi is integral over C m t plus delta t minus integral over C m at t. So, this integral evaluates as integral over C v dv plus integral over C s rho phi u dot n ds. So, the C v and C s are fixed quantities which you have selected. Now, how do you select in a given problem? So, we will see that this C v plays a role very similar to a free body diagram of your solid mechanics calculations. So, free body diagram over there and C v here, they play comparable roles. So, there is nothing unique about C v, you choose it so that you get the answers of interest. So, this capital phi and small phi, these get related to the natural laws or laws of physics as they are called at the continuum scale. So, mass, momentum and energy. Mass is m, momentum is mu and energy is I plus u square over 2 plus g z, where g z is a sample potential energy, is an example of a potential field. There could be other types of potential fields also. So, when you pick capital phi as the mass of the material, you know that d phi dt, the left hand side is evaluated for that mass and it is conserved. So, the time derivative is 0. So, conservation of mass. So, if you set capital phi as total mass, small phi is 1 and you d phi dt is 0, and you get an important result, the first equation of motion based on the conservation of mass principle as this integral equation. So, I mentioned last time that integral equations generally are harder to solve compared to differential equations. So, always drive towards reducing our governing equations, like the rigid body problem with m du dt etcetera. It is a differential equation. We want to reduce it to a differential form. So, that is enabled by replacing the surface integral by a volume integral. So, this is integral over C v del dot rho u dv, and then combining the two integrals, and then you may either let C v shrink to a point, or you may say C v is arbitrary, that means it is not prescribed. Since it can be anything, it follows that the integrand is 0. So, we got this differential form where rho is the material density. So, if the fluid medium can be treated as incompressible, that means its density does not change, whatever be the flow field, which is certainly very true for liquids, and for gases also. even though it seems as if gas is compressible, but you have to apply a lot of force to compress it, but it is compressible. But in many problems, gases also can be treated as incompressible. So, that we see as we go along, but for liquids it is a little more evident. If rho is constant, then del dot u is equal to 0. This is called a divergence free velocity field. So, conversely, if the velocity field is divergence free, then it is incompressible. You remember the interpretation of these terms. The first term refers to changes in density taking place in the material, while the second term is the difference between inflow and outflow. Okay. In terms of course, when you have rho, it is mass inflow, mass outflow. The difference between them, it is like saying if 10 students come in and 2 students go out, the student density in this room has gone up, right. But if 10 come in, 10 go out, then the student density is intact. That would be a number density. Sorry for thinking of students as particles. So, when you write a differential equation, it is for a small element. So, that is it local or global? Local, it is a local description of the flow field, the differential equation. When you write it in integral form, it is a global description of the flow field. So, that is the power of a natural law, that it holds at the local scale as well as the global scale, but not the particular, not the atomic level. So, looking at the integral form, so here I write local and integral form is global. So, we wrote it in the previous slide. So, this is, let us say, rho equal to constant. We have integral over C s u dot n ds equal to 0. Okay. So, the derivative of rho with time is 0, and then in the second term rho is constant, you take it out and then it cancels off. So, you can set up your problem, you can proceed towards solving for quantities like velocity and pressure. You are always trying to find velocity, pressure, integrate, find forces. So, you can either start with the integral form or you can start with the differential form. If you are looking for an exact solution, the differential form is what you would prefer to use, because you have learned differential equations for at least 4 if not 5 years. But let me illustrate to you that some results can be obtained quickly by working with the integral form. So, solving an integral equation is hard, but you can solve the integral equation approximately. So, this is probably a new idea, but it is a very commonplace idea. Approximate approaches estimation. For example, in many situations. I gave you an example of a pump required to raise water through 6 floors. Does it require 1 megawatt power, or does it require 1 kilowatt power, or does it require 1 watt power? That is an estimate. Okay. So, suppose you say I do not know, and you, just to be on the safe side, I want to buy a 1 megawatt pump. Not only is it expensive, its running expenses are very high, maintenance is very high, and consumes a huge amount of space. Why buy such a huge pump? If you knew it was 1 kilowatt, then it simplifies life quite a bit. So, we estimate. One of the important characteristic traits in engineering is to estimate, approximate, something we do often in the profession. So, can integrals be approximated? So, it is no magic about it. So, suppose I have this integral a to b f x dx. You want to evaluate this integral. If f is given to you, then you can use hundreds of techniques and probably evaluate. But an approximation of this integral is simply f bar, the average value of f over the region or the length a to, over the distance a to b, multiplied by b minus a. Okay. So, you can work with this average value. Okay. So, when you solve this problem, you substitute f bar into b minus a in your governing equation, then the answer you get will be f bar, not the function f x. So, you have approximated. Okay. So, f may have some variation, but you get its average value in the calculation. So, suppose it is let us say a volume integral where f now depends on, okay, just to use the same notation as before. Let us say you evaluate this function that can change from point to point in a given volume. You find its average in the volume and multiply it by the volume. So, I am using this crossed V for the volume of some entity, such as the control volume. So, we can use simplifications of this type and evaluate integrals and derive answers of importance very quickly. So, let us take an example. It is an example for illustrating the conservation of mass principle. This example, it is flow through a tube. This tube could be vertical, horizontal, it could be a tube used to pump water from the ground level to the 6th floor of your hostel, or it could be a pipeline conveying natural gas from some refinery to maybe this. We also have piped natural gas. So, there are pipes. It is just that the dimensions keep changing. There is also a pipeline that brings water from Ganga barrage to our campus. So, it is just a tube, and flow is from left to right. It has some radius just a tube. So, to carry out the analysis of flow taking place through the tube, what do you have to do? What do you think is the first step? Now, I will not repeat it, but it should be second nature to you, but you have done this earlier. You set up a free body diagram. So, here what do you do? Set up a control volume. Okay. Set up the control volume for analysis. So, this control volume will contain the fluid medium, it will not contain the tube. So, control volume is inside the tube. Now, should the control volume touch the walls of the tube? We will see that if you choose the control volume that way, it helps in the evaluation of the integral. So, the control volume is inside the tube. So, now I show the control volume separately. So, let me call the corners A, B, C, D. So, the left hand side, this plane is a flow u 1. So, this is plane 1, this is plane 2, and flow going out is u 2, and the wall which is around is 3. So, since we are talking about pumping water, let us work with the incompressible form. Where rho is constant. So, then integral over C s u dot n d s. This is 0. So, this can be evaluated. Now, C s is in 3 parts. It is 1 plus 2 plus 3, 3 parts to the control volume. 3 is that surface of the tube. Suppose you do not pick 3 as the surface of the tube, it will have its own consequences. We are not forced to pick 3 as the inner surface of the tube, but you will see that it has an advantage. Is equal to integral over 1 plus integral over 2 plus integral over 3. Integral of what? U dot n ds over that part of the surface. Now, u dot n is the velocity component normal to the surface. So, on the if you pick 3 to be the inner surface of the solid wall, u dot n, there is no flow piercing through the tube. So, it is 0. So, that is a simplification. If you pick your control volume with 3 lying inside the flow, then that velocity component may or may not be 0, you do not know. But if you make it coincident with the tube, it is 0. So, you can quickly see here is 0 for the third surface. Now, for 1 and 2, see for 1 the unit outward drawn normal is leftwards. So, u dot n will be minus u 1. Okay. So, using that approximation, now u, this is not being claimed that u is constant on the left plane, but we are replacing it by an average value. The average value is u 1. Okay. So, that is in the spirit of an approximation of the integral. I have to give a small disclaimer. We will see that this f bar, see this when you evaluate an integral in terms of its mean value, that is exact, right. You know the mean value theorem, f that f tilde not f bar, that f bar, that is an exact result, but later we will see that average also is evaluated in an approximate manner. So, then it becomes approximate. Hey, is the mic working? Huh? You may not. Is it working? So, let us evaluate. So, on the left side it is minus u 1 a 1, then for the second surface it is plus u 2 a 2, and the integral over the wall is 0. So, this is equal to 0, which is just u 1 a 1 equal to u 2 a 2, that is the flow going in is equal to flow going out. Okay. So, this requires the medium to be incompressible. If you think compressibility is important, then let us evaluate the integral. For suppose it is suppose you want to approximate this integral equation in algebraic form. What is the first term? The first term will be the derivative averaged over the control volume. Okay. So, this term averaged over the control volume multiplied by volume plus minus rho 1 u 1 a 1 plus rho 2 u 2 a 2 equal to 0. So, rho u a is the mass flow rate. So, mass flow rate going out minus the mass flow rate going in plus the changes in density taking place within the medium will all add up to 0. So, in algebraic form. So, this quantity. So, how do you evaluate, let us say the first term, you may approximate it as the derivative of the space average density. So, that is an approximation. Okay. The average of the time derivative and the time derivative of the average may not be exactly equal, but you may approximate it that way just to move forward in the calculation. Okay. So, it is a so these integral equations can be used to estimate maybe changes in density, maybe you can find out the flow going out if you know the flow going in. So, a variety of problems can be solved by simplifying the integral equation. So, we will look at some more examples as we go along. So, let us change the page, because now I want to move on to the momentum equation. Wherein capital phi is the momentum of the material contained in the control volume, in which case if you write capital phi as momentum evaluated of course in cm, but cm coincides with cv. So, that is how the evaluation is facilitated, and phi is you remember that capital phi is integral rho phi u rho phi dv, right. Rho dv is mass. So, mass times velocity is momentum. So, substituting these quantities in Reynolds transport theorem and applying Newton's second law of motion, where d phi dt is replaced by sum of all external forces F is equal to integral over C v. So, for phi we write u d v plus integral over C s rho u u dot n d s. So, this is the momentum equation. Now, what is this F? It is the sum of all, it is not just one force, it is sum of all external forces acting on the fluid in C v. Okay. So, it is force acting on the fluid. I am saying that because you also have solid adjoining solid surfaces. Okay. So, you will have to transfer information about forces acting on the fluid to forces acting on the solid. That is one extra step you have to carry out. This equation will give you only forces acting on the fluid medium. So, let us look at the, if steady, if you say flow is steady, then the first term is 0. And if it is incompressible, okay. So, I will expect you to remember these expressions when you do problems. So, on Wednesday we will do some problems, tutorial also you will do problems. So, by the time you have practiced a few of them, these expressions will become second nature to you. So, if you remember, for mass balance we had converted the surface integral into a volume integral. So, here also you can write it as del dot rho u u, and then this entire right hand side will be f equal to integral over C v del the derivative of rho u with time can be written as rho times derivative of velocity plus u times the derivative of density, right. It's differentiation of a product of two functions. And then rearranging terms. So, this will be u dot well, there is no dot here. Plus rho so, this is just writing that expression, almost analogous to the mass balance equation. Now, how much is the first term? That time derivative of rho plus del dot rho u. How much is it? Can you tell me how much it is? How much it is in one voice? 0. Somebody said 0. Why 0? Because of conservation of mass, right? That was the conservation of mass equation. So, the first term is 0. So, you are left with the second. Okay. So, the momentum equation is also expressed as now, what is rho dV? Rho dV is elemental mass, right? Density times volume. Rho dV is elemental mass. And then what is Newton's second law of motion? Quickly, when somebody asks you, what is Newton's second law of motion? You say F equal to ma, is it not? So, just looking at this expression, if this is F equal to rho dV is elemental mass. So, the quantity in brackets, how much is, what is it? Acceleration. Does not look like acceleration, but it is acceleration that we will study a little more as we go along. So, this is, so you are not saying anything new at all. This is simply Newton's second law of motion in a structured mathematical form involving flow quantities, particularly velocity and density. Okay. And that is equal to sum of all external forces acting on CV on the fluid medium. Okay. Of course, if the flow is steady, then the time derivative of velocity is 0 and you are left only with the second term, which again is equivalent to what we had here. So, this of course, so okay, so let us look at an example again. Let us apply the momentum principle to flow through a tube. Pick a control volume, show it separately, label the corners, identify the surfaces, choose surface 3 to coincide with the wall, so that u dot n is 0. It will simplify your integrals. This flow coming in, flow going out. Okay. This is CV, this is CS. So, let us say flow is incompressible. Then F is equal to rho integral over CS u, what was it? It is u bracket u dot n ds. So, split the integral into 1, 2 and 3, u dot n is again 0. So, this third integral is 0. Now, this equation, it is a vector equation. So, naturally our interest will be in the direction along the axis of the tube. Okay. So, suppose we specialize this equation to the axis of the tube. So, then, so you are looking at the component along the axis of the tube, and then we write F. F is the force acting on C V, and this is now the axial component. This is called axial component. For integral 1, once again n is directed to the left, flow is to the right. So, you write it as minus u 1 square, right, and ds will be a 1, that is an evaluation of the integral. So, there also you will have u square average, what you will get is u square average, that is exact, but you approximate it as u 1 square. It is the average of the square is replaced by square of the average. So, let me repeat it once more. Let us say you have an integral of this type over 0 to 1, let us say. So, this is u square average into 1, this is exact, and the approximation is square of the average. So, that way this becomes rho minus u 1 square a 1 plus u 2 square a 2. Now, you realize a 1 is equal to a 2 equal to a, and u 1 is also equal to u 2 y. That is the result we got from conservation of mass. So, how much is this f? It is 0. So, what does it mean? That we will see as we go along. F is equal to 0. So, how much is the acceleration of the fluid? 0. The fluid is non-accelerating, which is why you have a vertical tube, and then whatever flow is going in is also coming out. It is not accelerating. But is it a useful result? We will see it is very useful. In the very next class, we will see it is very useful. Now, suppose a 1 is not equal to a 2. So, let us say you have a geometry like this, where a 2 is greater than a 1, or you have a geometry like this, where a 2 is less than a 1. If a 2 is greater than a 1, that the name given to it, what you have a tube, but if a 2 is greater than a 1, that geometry, what is it called? It is called a diffuser geometry. Diffuser, that is a technical term for it. Tube is also a technical term. And then when a 2 is greater than a 1, it is a diffuser. If a 2 is less than a 1, what name would you give it? Compressor? No. Compressor is a device. A 2 less than a 1, it is called a nozzle. Okay. So, in these geometries, f will not be 0. You can work it out, because you can't take that a out. So, we will complete these problems next time. Okay. So, but pay some attention. So, we are talking about momentum equation and approximate evaluation of the integrals involved and estimating forces. So, this is all from chapter 3 of your book. All right. So, problems assigned will also be from chapter 3. Okay. So, we will stop now, and if you have a class you can carry on.